Greetings and welcome to Hobo University, where your professor will teach you what you need to know to get started with solar, batteries, and understanding electricity. In our previous lessons, you learned about volts and amps and why they are important. Today's lesson is going to focus on watts and what are watt hours and what are amp hours. So if you haven't watched the previous lessons about volts and amps, there are going to be links in the description of this video. You're certainly going to want to review those lessons first, as comprehending watts requires a basic understanding of both volts and amps. By the time you finish this series, you should have the answers to all your questions regarding these concepts. So let's get started.
HOBOTECH.
So the big question is, what are watts? Why are they important in electricity and in electrical circuits? Now in physics, a watt is a measurement of power, or the amount of work done over a period of time. Now most folks have heard of horsepower. That's the amount of power it takes to lift 550 pounds 1 foot in 1 second. So to lift this 1 foot in 1 second, that's 1 horsepower. I bet you a lot of people don't know that's what a horsepower means. Apparently back in the day, that was the equivalent amount of work that a typical workhorse could do. So that became the standard. So in electricity, it's basically the same thing. We can convert an imperial horsepower into watts with the magic of math and get 746 watts electrical. So a 750 watt electric bike is roughly 1 horsepower. So a lot of you know there are a lot of 750 watt bikes on the market, and that seems to be the cutoff for a lot of them. That's because the legal limit in a lot of areas is 750 watts or 1 horsepower. Now, if you want to get really technical, a watt is the measurement of 1 joule of work being done per second. But I don't want to get too crazy in the physics because that's beyond the scope of this lesson. To keep things simple, we're just going to call a watt the amount of work being done at any one instant in time. The unit was, of course, named after the inventor James Watt, which is why the abbreviation we use for watt is capitalized. So if you're going to say something is a watt or watt hour, so you'll notice the W is always capitalized, even if there is a small k in front of it for kilowatt hours, because this is named after a real life person. So we always capitalize the W in the abbreviation when we talk about watts. So why is understanding watts so important? Pretty much everything sold in the electrical world is based on either amps or watts. Watts actually tells you the bigger story. Like how many watts an appliance uses directly tells you how long a battery is going to last in an off-grid system. How many watts a solar panel produces directly influences how long it takes for the battery you just used to recharge. Now many folks, especially old school electricians, always want to talk in amps. They like to talk in amps because that's what they learned when they became electricians. And there's a big reason why they use amps and not watts. A lot of times somebody who has electrical knowledge or is an electrician is going to ask you, how many amps is that solar panel, not how many watts? Now, if you answer 5, what does that tell somebody? Well, pretty much nothing, unless you already know the voltage of the system. Because speaking in amps always requires the knowledge of voltage too. Otherwise, the unit 5 has no meaning. So why do electricians speak in amps? Because they work mostly in 120 volt AC systems, which is the standard in the US. This is the language they speak in, because even if you're running a 240 volt split phase system to run a large appliance like a stove or an electric dryer, that also runs on 120 volt lines. So that means if you need a 50 amp line for an electric stove, that means 50 amps for each 120 volt circuit. However, when referring to DC power, which is generally all we use in the solar and battery world, you must know both amps and volts if you want to describe the amount of power a load is consuming or a solar panel is producing. So how do we calculate watts out of amps and volts? Pretty easy. Okay, there's some very easy math that allows you to calculate watts, which is power, from volts and amps. And if you have any of those two numbers, you can calculate the third with any of these 3 formulas. So the primary formula is going to be watts equals volts times amps. And if you have watts and volts, you can figure out amps by dividing volts by watts. Same thing with volts. If you have watts and amps, you want to know what the volts of the system is, you take watts divided by amps. So of course, I'm going to give you some examples to explain what this all means. So say you have a 12.8 volt DC lithium battery that can output 100 amps. How many watts is that? Well, you know what volts are and you know what amps are. So you take volts times amps. So 12.8 times 100 equals 1280 watts. That's why if you buy a 100 amp hour lithium iron phosphate battery, it's 1280 watt hours. I'm going to get to watt hours in a moment. So next example, you have a 6,000 watt inverter. Say you're building a system for your home or a workshop, and you get a 6,000 watt inverter. So you want to know how many amps does it pull so you know what size cables to get, because you learned in the last lesson, amps are super important to know because that tells you what size cables you're going to need. Now, this problem actually has two results. Since an inverter pulls DC power in to output AC power into your home. So we actually have two results for this. Since it's rated to output 6,000 watts of power, and that's going to be at 120 volts AC, you would take 6,000 divided by 120 to get the result of 50. So on this side, for the AC output, you need 50 amp cabling over 120 volts AC. Now the DC input side is going to depend on what the voltage of the battery is. Now in this case, since it's a 6,000 watt inverter, it's pretty much going to be 48 volt battery. And I'll show an example, a reason why you were going to pick a 48 volt battery in this case in a little bit. So again, you take 6,000 watts divided by 48 volts, and that gives you 125 amps. But let's pretend instead of a 48 volt battery, what if it was a 24 volt battery? So now you take 6,000 watts divided by 24 volts, your answer is 250. So by cutting the voltage of your battery in half, you double the amount of amps required to go through these cables. Now the difference between a 125 amp cable and a 250 amp cable is much bigger cabling, much bigger, much more expensive cabling, much harder to bend, much harder to work with. You need bigger lugs. It's much bigger pain in the butt to deal with 250 amp cable than a 125. So that's one of the main reasons why you want to go with the 48 volt system if you're doing 6,000 watts or larger inverters. So you see, it's really important to know both the input and output power in some cases when you're designing your system. This next example, we're going to use a 50 amp solar charge controller. Solar charge controllers too both have an input and an output side. So say you have, these are two 100 volt solar panels in series. So they're 200 volts total, and they're 10 amp panels. So it'd be 200 volts at 10 amps. Going into the 50 amp solar controller. You want to figure out what's the best battery voltage to run and what size cables are you going to need to safely run these batteries. So this is a very, very common question. I get this all the time. That's why I'm using this as an example. So the first bit of math we need to do is figure out how many watts of solar panels we have over there. So we have two 100 volt solar panels in series running 10 amps. That'd be 200 volts because you add the volts times 10 amps. You get 2,000 watts. So this is a 2,000 watt solar panel array. So next you take the 2,000 watt solar maximum divided by the 50 amp controller. Because what you're doing is you're putting this 2,000 watts of solar into this solar controller. So 2,000 watts divided by 50 amps. That would be the voltage of the battery. Now they don't sell 40 volt batteries. So what you do is you step it up to the next one, 48 volts. So in this case, you would want to use a 48 volt battery, and that makes complete sense. Now say you decided to do a 24 or 36 volt battery. Well, you wouldn't be able to use the full 2,000 watts because you would do the equation backwards. You take 36 volts or 24 volts times 50, and you'd see you wouldn't be able to get 2,000 out of that. It would be much less. So in this case, a 48 volt battery is what you'd want to buy. So if you multiply these two numbers together, 50 times 48, you're actually going to get more than 2,000 now. That means you can actually put 2,400 watts of solar into this controller. So that means you might be able to add more panels in this situation because you have a little bit of leeway. Now, there's something very important you need to remember, and I did mention this in my previous videos. These solar charge controllers do have amp and volt limitations. So this solar controller might only be able to take 150 volts of panels. In that case, you couldn't do this. You would need something that can handle at least 200 volts or more. And you also have an amp limit. A lot of these are 15 to 20 amps. A lot of them are 15 to 20 amps. Of course, you can buy bigger, more expensive models that can do 30 amps, 50 amps, whatever. But a lot of the smaller ones are going to be limited to 150 volts, 15 to 20 amps. So just be aware when you purchase it, look for that limitation to match your solar panels. Okay, so if you wanted to know what amp size cables you need for this battery, how would you figure that out? Well, it's right there. The solar controller can only output 50 amps. It'll never output more than 50 amps. It's limited internally. Doesn't matter how many watts of solar you provide it, that number 50 amps in this case is your limit. So these black and red cables coming out going to your battery need to be 50 amps or larger. And you can use that chart that I showed you in the amp video to determine what gauge wiring you need, an AWG or American wire gauge for this particular battery. Never go too small. It's always better to go large. Go big or go home when it comes to cables. All right, now we're down to the good stuff. So what if you wanted to measure the amount of power stored in a battery, or even the amount of power stored, say, in a gallon of gasoline or propane? We still use watts for the amount of power, but we need to know how long can you use that amount of power before the stored energy runs out. The electrical standard is based on hours. That's why when you purchase a battery, they don't say it's 12.8 volts at 100 amps. They say it's 12.8 volts at 100 amp hours, because that's the number of amp hours the battery is. So what we need to do is figure out the amount of watts used over the period of 1 hour, or you guessed it, watt hours. Since we're talking James Watt again, we abbreviate that WH, capital W, lowercase h, and you figure out watt hours by simply taking the watts times the amount of hours. Or in the case of the battery, you're doing volts times amps divided by hours, and that gives you watt hours. All right, solar generators, portable power stations. We have our famous Jack Eddy. This time we have the Jack Eddy 1000. Now, a lot of brands market their products based on one of two numbers. It's either going to be the inverter size, which in this case would be 1000 watts, or the battery size, which in this case is also 1000 but watt hours, because we just learned that watt hours is the standard for battery storage size. 1000 watts is actually the amount of power coming out of the inverter. So when you plug into the inverter, the maximum allowed appliance that you can run is actually 1000 watts. So you cannot exceed 1000 watts appliance power. So your first question might be, okay, I have this Jack Eddy 1000, it's 1000 watt hours with a 1000 watt inverter. How long can it run? Okay, get this question every single day. So if you're going to actually pull the full 1000 watts, say you're running a coffee pot or an instant pot or something that pulls 1000 watts, we'll say exactly in this case, and the battery inside it is 1000 watt hours, you take the watt hours divided by the watts and you get the number 1. That's the number of hours that this product can run. Let's go with another example, a little more complicated math. So say you have a teapot that you're running on the Jack Eddy that's 200 watts. Now I know it's a horrible teapot, but I never said I was an artist. So the teapot runs 200 watts. It has a 1000 watt hour battery. So the math is very simple. You take the 1000 watt hours of the battery, divide it by the 200 watts of the appliance. Your answer is 5 hours. 1000 divided by 200 is 5 hours. Another thing you can consider, when you do this equation, what you're trying to do is get rid of the W's. They cancel each other out. So in algebra, they teach you if you have a unit on the top and a unit on the bottom of your equation, it cancels each other out. And that's what we're doing here. We have watts on the top, watts on the bottom, cancel them out. You're solving for hours, which is exactly what we're doing here. So 1000 by 200 equals 5 hours. Here's another question I get all the time. I have a certain size air conditioner. We're going to say this is a 1000 watt air conditioner. It runs 1000 watts. When it's turned on, the compressor is running and it's blowing cold air in your face. It takes 1000 watts. This is just an example. This would be a pretty large air conditioner, probably like a 12 or 15,000 BTU to pull that much power. But say you have a 15,000 watt BTU air conditioner in your RV that pulls 1000 watts, and you want to run it for 8 hours during the heat of the day, and you're like, I have no idea how to figure out how much battery do I need to get by 8 hours at 1000 watts. Now, if you remember the equation I just told you here a moment ago, this is super easy math. So 1000 times 8 hours, because you're taking watts times hours, you're creating watt hours. Watts times hours equals watt hours. So in this case, 1000 times 8, 8,000 watt hours. Yes, that's a heck of a lot of battery. How many 100 amp hour batteries, or let's just say how many amp hours of batteries, do you need in that case? Well, we know that lithium batteries, and all my audience is just using lithium batteries, right? None of you guys are still on lead acid, I hope, because those are garbage, and Lithium batteries now, 100 amp hours, are under $200. You can get them all over the place now. I have a bunch I reviewed, a bunch on my website if you're interested. They're all 12.8 volts. You can get 24 and 48 volt lithium batteries. Let's say this is for an RV and you want to stick to 12.8 volt batteries. 12 volt batteries because everything in your RV, your furnace, your fridge, everything runs on 12 volts. Let's just use that as an example. You have a 12.8 volt RV. You want to know, how many amp hours of batteries do I need in order to run this air conditioner for 8 hours? So you take your 8,000 watt hours divided by 12.8 volts, because we already learned that in order to solve for amps, you need watts and volts. So you take the watts divided by the volts, and you get 625 amps. And that's how many amps, but you have to also add the hours in because we're talking watt hours, not just watts. Remember, there's a difference between watts and watt hours. Watt hours is the battery storage capacity, so you have to add hours onto that. Guess what? You need 625 amp hours worth of 12.8 volt batteries to run this air conditioner for 8 hours. This is very easy math that eludes a lot of folks. So that's why I'm doing this particular lesson, spending so much time on this, because a lot of people can't figure this out. This is very easy to do once you understand what you need to divide and multiply. And you can always go back to those formulas I showed you a few minutes ago. So you need 625 amp hours to last the 8 hours. Now, of course, you can change the hours, you can change the size of the air conditioner or the appliance. This applies to every appliance. AC, DC, doesn't matter. All this works for AC or DC electricity. So what about kilowatt hours? Most of you read your electric bill and you see, oh, I used 1,000 kilowatt hours last month to power my house. Okay. Most people have no idea what a kilowatt hour is, but I just explained to you what a watt hour is. So a kilowatt hour, kilo means 1,000. This is how many 1,000 watt hours. So if you want to get complicated here, that would be 1,000 times 1,000, or 1 million watt hours. Okay. That's why they use kilowatt hours, because could you imagine opening your electric bill and says, you used 1 million watt hours. You'd be like, 1,000 sounds much better. And they charge you per kilowatt hour. So where I live in Arizona, they charge about 13 cents per kilowatt hour. And that's 13 cents including all the taxes, because I factor that in too. The real rate's probably like 9 cents. But once you factor in all their absurd taxes for everything, and just having the utility turned on is also a charge, I figured out my electric is about 13 cents per kilowatt hour. That's going to be way more in California, way more on some of the northeastern states. Hawaii, you guys are paying like 50 cents a kilowatt hour. I know San Diego is like something ridiculous, 40 something cents per kilowatt hour. I mean, you guys are going to go completely broke just trying to power your homes. In my case, my utility charges me 13 cents for one of these. So if I actually use 1,000 of them in 1 month, that math is pretty easy. You do 13 cents, which actually it would be 0.13 because that's a dollar. If you want to figure it out in dollars, you do 0.13. Move the decimal 3 places, 1, 2, 3. My bill would be $130 for 1,000 kilowatt hours. Pretty simple. Okay, now you know what kilowatt hours are. The next big question I get all the time. I have a refrigerator. I want to power off my Jack Eddy. I want to know how long can I run my refrigerator before the battery dies. So this is very easy to figure out because pretty much every modern refrigerator is going to have a tag, one of those yellow energy tags that tells you how many kilowatt hours per year your refrigerator uses. Now that includes the ice machine, the defrost cycle. That's the total power usage for the year. So I'm going to use, in this case, 400 kilowatt hours. That's about average. It's not too high, not too low. This would be for like a regular size residential fridge. It's not a piece of junk that's somewhat efficient. So how do you figure out how many watt hours per day? Okay, math again is very simple. What we do is we take the 400 kilowatt hours divided by 365 days in the year. This will give you the number of kilowatt hours per day, which in this case the math comes out to 1.1 kilowatt hours per day. So in this case, we're rounding down to 1.1 kilowatt hours per day. So if you take this and multiply by this, you get close to 400. This is how much power that refrigerator is going to use in one 24-hour day. How many watt hours is that? Well, you guys already know that a kilowatt hour is 1,000 of these. So you just multiply that by 1,000 and you would get 1100 watt hours per day. So that 1,000 watt-hour Jack Eddy will not power this refrigerator for a full 24 hours. But we want to know how long would that 1,000 watt-hour power this. So in that case, you would take the 1,000 watt-hours from the Jack Eddy and divide it by the 1,100 watt-hours. That result would be 0.9, approximately. 1,000 by 1,100, 0.9. So this is the number of days. So to convert this from days to hours, you take your 24 hours in a day times 0.9, and that comes out to about 21 hours. So I'm just estimating, this is a rough, it's not gonna be exactly 21 hours, but this gives you an idea. You can run this refrigerator on your 1,000 watt-hour Jack Eddy for 21 hours before the battery dies, your refrigerator dies, and all your food gets ruined. Now you guys are the expert in this. So anytime anybody asks me to answer this question for them, I'm gonna point them to this video so they can figure out the math on their own. So that's it. Hopefully you've watched all 3 lessons about amps, volts, and watts, and now understand a bit more about that magical force we call electricity. At least now you can figure out on your own what voltage and wattage solar panels you want to buy, what size batteries to get, how to figure out what solar charge controller you need, what battery voltage system you should run, what gauge cabling you need, how to figure cable voltage drop over distance, how to figure out how long it takes to charge and discharge a battery, how to figure out run times for all your power station products. Whew, that's a lot of stuff. But now you know, and knowing's half the battle. So now that you've graduated from this class, get out there, put your diploma to good use. Thanks for watching. That's all for now. Till next time.
Odin commands you to like and subscribe, and clean my litter box.